So having seen what an abstract data type is, let's try to see how object-oriented programming, which is the main focus of this course, relates to the notion of an abstract data type. So an object is essentially the same thing as an abstract data type in the sense that it has some hidden internal data along with a set of public operations. And as we would expect from an abstract data type, all the interaction that we do with such an object is through the operations. And in object-oriented programming, there are many different names given to these operations. So very often they are called messages or methods, or in some programming languages they are called member functions and so on. But they all mean the same thing. These are essentially the public functions which we use to manipulate the data inside an object or to find out information about the data inside an object. So an object provides a uniform way of encapsulating different combinations of data and functionality. So it does not mean that an object has to be very complicated. For instance, supposing we want to represent a counter. A counter is essentially just an integer with an increment operation. So an object can consist of just an integer inside and a public function to increment this integer or to reset it to 0. Or at the other extreme, we could have a large volume of data inside an object. For instance, we could have the entire contents of our disk, an entire file system, or we could have a large database with multiple tables. And we could manipulate this entire database or this entire file system as a single object where the data is the information contained in the file system or the database, and the operations are those that we choose to allow on this object. So we will look at 4 distinguishing features that characterize object-oriented programming. The first, of course, is abstraction, which is related to this notion of an abstract data type. But where object-oriented programming goes beyond just mere abstract data types is in the fact that it allows what's called subtyping. So there is a hierarchy of types. And along with subtyping comes an important idea called dynamic lookup, which we shall explain. And there is also a related idea to subtyping called inheritance, which is to do with reusing implementations. So before we get into these 4 specific aspects of object-oriented programming, let's see where object-oriented programming first arose. So the first programming language which actually introduced objects in the way that we use it now is a language called Simula, which came out in the 1960s. And the name suggests Simula was used as a simulation language. So what would you do typically in a simulation? In a simulation, you have a system which you are abstractly running in a simulation. So the system has certain activities or events, and you keep running these events and exploring what happens as a result of these events and exploring the evolution of the system. So the typical run of a simulation starts like this. You start off with an initial event, okay, which you put into a queue. So this is a queue of events that remain to be simulated. So at every point you take the head of the queue, the first event E in the queue, and then you simulate it, right? So you do whatever effect that event has on the environment that you're trying to simulate. And in turn, this event might trigger other events. So you trigger these events by putting them in the queue. So when their turn comes, you will explore their effect. So though in a real life system, these events will be happening concurrently, simultaneously, whatever, in a simulated system, you execute them in a particular order following a queue. So what is the problem with this? Well, the first thing is that the queue is a regular data structure. So normally when we have a queue or a stack or an array or any sequence that is well typed, all the elements of this data structure may be the same type. Now events in such a system will typically be of many different types. So how are we going to accommodate all the different types of events into a well typed queue? The second thing involves this step. So when we say simulate E, this means we have to perform the actions that E performs on its environment, the environment that we are simulating, and this will differ from event to event. So one way to do this is to have an elaborate checking of cases. If E is of type E1, do this, if E is of type E2, do that, and so on. But this would be very tedious to program and very tedious to keep track of in our code. Suppose we add a new type of event, for instance, we will have to change our code to add one more case. So what we would like is that each event, if it is an abstract data type of itself, it has with it a method or a function or a member function or whatever, which tells it how to simulate itself. So we just activate this function on the event, and each event in some sense knows how to simulate itself. So this is the kind of model that Simula was trying to create, and this is the reason why Simula needed objects, right? It needed some way of telling each event to simulate itself without going into this elaborate description of which type of event it is at the time of calling the function. So with that background, let's get back to these 4 aspects of object-oriented programming that we introduced in the beginning. So the first is abstraction. So we said that objects are similar to abstract data types, so they will have a public interface and a private implementation. So usually the private implementation is the data that is stored inside. We don't normally allow an external piece of code to access this data directly. And there will be public functions which access this data, manipulate it, update it, report quantities based on it, and so on. And the whole principle of separating out the public interface from the private implementation is that if we, for whatever reason, change the private implementation, we might make it more efficient, more scalable, or any such thing. From a functionality point of view, the user of the public interface should not see any difference. So any code that uses this object should not have to change just because we have changed the way this object is implemented. So this is like a component in a system that we talked about when we were doing this kind of refinement. So when we elaborate a component and make it more complex, the remaining components continue to interact with it in very much the same way. So the reason that object-oriented programming is slightly different from the kind of programming that we are familiar with is that normally when we write programs traditionally, we concentrate on the control flow, we concentrate on what is to be done, we concentrate on the operations, we define functions, and then the data is used to keep track of the state of the computation. Now, object-oriented programming reverses in some sense the focus and says, let us first understand what data we are trying to keep track of. And based on this, we ask what we need to do to manipulate this data. So what are the requirements for the data? So this makes a lot of sense if you're building a system, for example, like a banking system. So you need to ask yourself, if I'm building a banking system, what is the kind of data I need to keep track of? So I will need to keep track of information about bank accounts, about customers, maybe about transactions. And then we start asking how to keep this information, in what format we should keep it, and what are the allowed interactions and operations on these data things. So this is the data-centric view of programming, which gives rise to this object-oriented methodology. So one thing to keep in mind is that we generally have to build a complex program by breaking it down into smaller tasks. So we call this stepwise refinement. So we saw that you could stepwise refine a task by breaking it down into subtasks. So you make a larger, more abstract task into more concrete tasks. So instead of saying print a table, you would explicitly write a loop saying for each element in the table, print it, and so on. And at the same time, we may also need to change the data structure that we are using. So we saw this in the bank account example, where we had to move from keeping just the balance to keeping the transactions. And there the difficulty was that once we moved to keeping transactions along with the balance, all the functions which manipulated bank accounts needed to change their behavior. So we needed to somehow keep track of this change across multiple functions. Now, if we are doing this in this abstract data type or data-centric world, all the functions that manipulate a piece of data will be actually coded along with that data. So when you change the internals of an object, if you need to change the functionality of some of the functions, it comes automatically because you know that the internals are changing because they're all in one place. So from a kind of, you might call it a bureaucratic administrative point of view, it is much easier to track the changes that occur because of changes in your data refinement on the functions that you're writing. So let's move to this aspect of object-oriented program, which takes us slightly away from just abstract data types. So let's get back to the Simula event queue. So we said that a Simula event queue will hold values of a fixed type, but in practice, what is in the queue is a collection of different types of objects, right? So we have a kind of heterogeneous collection of objects. So how do we reconcile this combination of wanting to have a queue which has a fixed, well-defined type, at the same time allowing it to hold a collection of different types of objects? So the solution to this is to allow what is called a hierarchy of types. So we can say that one type is a subtype of another type. So what do we mean by subtype? Well, we mean that it's a more specialized version of that type. So whenever A is a subtype of B, in any context where we require a B, we can also use an A. So a subtype has as many capabilities as B and more. So if you are confused about the terminology subtype, you should think about subsets, right? If X is a subset of Y, it means that anything that is an X is also a Y, but not everything that is a Y is an X, right? So everything that's an X is a Y. So similarly, everything that is an A is also a B, but there are some B's that are not A's. Right? So this is what subtype means. So A is more specialized than B, but it can do everything that B is expected to do. So in particular, if there is a function f that you can call on a type B and A is a subtype of that type B, then that function f will also be valid on A. So syntactically, if you're just thinking in terms of type, it is legal to call function f on A if you have an A instead of a B. So if you know that A is a subtype of B, you are guaranteed that the functions that are applicable to B will also be applicable to A. But now is a big difference. The implementation of f could be different in A, and this is what is happening in this Simula queue. So you have a kind of higher level maybe event which has a simulate function, and every concrete event which sits inside the queue is a subtype of this event. So all these event types also have a simulate function, but each of them has a simulate function which is specific to itself. So in this way, when I call an event from the queue and I ask it to simulate itself, it will call its own implementation of simulate. So the call will be legal because of the type, and the action will depend on what type of event it is. So this aspect is what is called dynamic lookup. So whether a method or a function can be invoked on an object is a static property. So this is like type checking, right? So once we have defined type B, we know all the functions that are associated with B, and if A is a subtype of B, and this is something which is syntactic, it's part of the program code, you will declare A to be a subtype of B, then all the functions of B will naturally be available for A. However, how these functions behave when you invoke them on objects of type A will be dynamically determined by the type of object it is. So I might have more than one thing which is a subtype, I might have more than one type of event. So each subtype will possibly have its own implementation of these functions. So in our simulation queue example, every event supports a simulate method, but the action that the simulate method triggers in terms of updating the environment depends on the type of event. In a different example, supposing we have a program which is a graphical program, so we are trying to manipulate some objects on the screen, there will be some shapes and there will be some other things which we want to put together. So imagine a kind of image editing program. So here we can change these objects, and then periodically we might want them to redraw themselves according to the changes, right? So each object can just be told to redraw itself. So redraw is like simulate, and each object, depending on the nature of the object, knows how to redraw itself. So this is again best done in this object oriented thing where we have this dynamic lookup. So dynamic lookup says you have the right to invoke a function on an object because the object satisfies the correct typing requirement, and what that actual operation performs depends on what that object is at runtime. So this is different from what we sometimes see in programming languages, which is called overloaded, where we use the same operator or the same function on different types. So a simple example is when we have this plus operator, right? So plus operator in almost any programming language can be applied to two ints or to two floats. Now from a mathematical perspective, an int or a float is a number, and we know that plus represents addition. So mathematically really there is no difference between plus on ints and plus on floats. But of course, we know that representation wise, because of the way that bits are stored and all that, ints are stored differently from floats. So the algorithmic operation of adding two integers stored in binary is different from the algorithmic operation required to add two floats stored in binary. Nevertheless, when we use it in our program, we don't want to write two separate things, a plus I and a plus f, so we just use a plus. And which plus is used and which internal algorithm is used to add these values depends on the static type associated with the variables we're trying to add. So if it is integers, it will use the integer algorithm for addition in terms of bit strings. If it is float, it will use the float algorithm. But this is static, right? So overloading happens when we apply different functions with the same name to different types, and the type of the value as it is declared determines which interpretation of this function is going to be used. Now, in dynamic lookup, this is done at runtime. So, one of the properties of subtyping, as we will see, is that you can declare a variable to be of the parent type and assign it to be an object of the lower type. So, for instance, if A is a subtype of B, then so A is, you should think of it as A is a subtype of B, and now I have declared a V to be of this type. I can actually assign V to point to an object of type A. So, although statically the compiler believes that V is of type B, at runtime the value stored in V is actually of type A. So, now if I take a function which is defined for B and I execute it on the object stored in V, it will not take the definition based on the type of V, which is capital B. Rather, it will take it based on the type of the object that is stored. So, at this time there is an A object stored in V. So, A has its own definition of whatever function I want, and that will be dynamically chosen. So, this is what dynamic lookup is all about. Finally, let's look at what's called inheritance. So, inheritance is a fundamental property of software development, which is that if you have something you have already written, you would not like to rewrite it, right? So, all over the place we try to reuse the code that we have used. So, in particular, when we are defining data types and data structures and so on, we would like to reuse implementations to the extent possible. So, here is an example. Supposing that we are trying to keep track of different types of employees in our organization. So, we might start with a basic type employee, an abstract data type which stores information about a basic type employee, which has basic personal data like their name and various things, maybe also their date of joining. Now, we might want to keep extra information about some types of employees. For instance, we might have managers whom we want to treat differently in some parts of the code. So, for a manager, we would like to add some functionality. So, maybe we might want to have some information about the date of promotion. Maybe all employees who are not managers have the same designation, but managers come in different types. There are assistant managers and there are senior managers and so on. So, we might want to know their date of promotion, their exact role, how long they have been in the current role and so on. But every manager is still an employee. So, every manager actually still has personal data, had a date of joining and so on. So, whatever we have defined for an employee can carry over to a manager. We don't have to rewrite those parts. The way of calculating, for example, the date of current seniority in terms of years of service will be to subtract the date of joining from today's date. Now, this is the same whether the person is an employee of a normal type or a manager. But if I want seniority in the current role, it refers to date of promotion, which does not make sense for employees, it makes sense for managers. So, in this way, a manager has additional functionality, but for the functionality that overlaps with an employee, we would not like to rewrite it. So, we would like to reuse that code. So, normally when we create hierarchies of types in a programming language, we only have one way of defining this hierarchy. So, we already saw that we have this hierarchy referring to subtyping. A is a subtype of B, which says that in every context where we want a B, we can substitute an A instead. So, A is a more specialized version of B. So, this goes hand in hand in most programming languages with inheritance. So, if we want to copy some code from B, or not copy but actually implicitly reuse it, then A should be sitting below B in this hierarchy. So, A can inherit from B. So, in the earlier case, we would have employee as a parent type, right, and we would have manager as a subtype. So, manager would inherit from employee. However, philosophically these are two different things. So, subtyping tells us something about whether a function is legal or not. So, it is a static property. If there is an f which is defined on the parent type B, then A must be able to do f. Right? How A does f is a dynamic property, but the fact that A can do an f is a property of its static type, right? The fact that it is sitting under B. However, so it's really a property of interfaces, which functions are legal and which functions are not. Whereas inheritance is a relationship of implementations. I am reusing something which I already have in B in the code for A. So, if B has defined some variables, then A can make use of those variables because A will also have access to those variables. So, to explore this difference between subtyping and inheritance, so here is a nice example. So, a double-ended queue or a deck is a queue in which you can add and remove from either end. So, let us say that this is the front and this is the rear, right? So I can insert in the front, or I can remove the element in the front. I can delete in the front, or I can insert in the rear and I can delete from the rear. So it has still some limited functionality. It's not a list. I cannot arbitrarily put something in the middle of a deck, but I can do it at either end. I can either insert at this end or that end. I can remove it. So it has 4 different operations, 2 inserts and 2 deletes. Now using this, I can easily implement a stack or a queue. So remember that a stack in this terminology would actually always operate only at the front, at the top, right? So this is a stack. And a queue, on the other hand, would insert at the rear and delete from the front. You join at the end of the queue and you leave at the beginning of the queue. Now if we had a deck, then these 2 data structures that we need to implement can be implemented by just choosing 2 out of the 4 operations that a deck supports, and for the rest the deck has a sequence of values and a stack and a queue have a sequence of values. So we can implement a stack or a queue easily using a deck. So in the sense that we are talking about reusing implementations, we can say that stack and queue are classes which inherit, or objects which inherit from the object deck. But if you think about interfaces, they are not subtypes, right? So supposing I want to declare that stack is a subtype of deck. So remember that if A is a subtype of B and if F is a function of, so if A is a subtype of B, right? And if I have a function here, then I must also allow that function here. This is a static property of subtypes. So now we look at this deck, right? So deck is sitting on top, right? And it has 4 functions. Now supposing I claim that stack is a subtype, but here I only have 2 functions, right? I only have the insert front and the delete front. So if I ask a stack to delete rear, this is a legal thing for a deck, but if stack were a subtype of deck, it would also have to support this operation, right? But it does not. So a stack has less functionality than a deck, so it cannot be a subtype of deck, even though it inherits from deck in the sense that we can use an implementation of deck to implement stack. And the same is true of queue, right? Queue also has only 2 of these things. It has an insert rear and a delete front. So if I want the opposite ones, if I want to insert in the front and delete in the rear, I cannot do it on a queue. So in this way, we can see that the interfaces of stack and queue are not compatible with deck. So in fact, it's the other way around, right? So deck technically can be treated as a subtype because everything that a stack can do, a deck can do. The 2 functions on stack are both available in deck. The 2 functions in queue are both available in deck. So if at all there is a subtyping relation, it's the other way around. So this is the real difference between subtyping and inheritance. So one is a question of whether you are reusing an implementation. The other is whether or not the interfaces are preserved. So to summarize, objects are very similar to abstract data types, and objects provide us a uniform way of encapsulating different combinations of data and functionality. So what we said is the data that is stored in an object can be very simple. It can be a single integer like a counter. It can be very complicated. It can be a database. But what really distinguishes object-oriented programming from abstract data types is this notion of subtyping. So obviously objects have abstraction like an abstract data type. So you would like to separate out a public interface from a private implementation. But you also allow yourself to arrange these types in a hierarchy. And by allowing yourself to arrange these types in a hierarchy, you can talk about a variable of a higher type containing a value of a subtype. And this allows you to create this heterogeneous queue, for example, that is used in Simula. And when you do that, it goes hand in hand with this idea of dynamic lookup. So you have a collection of objects which all share a common parent type. So they all have a common capability, but the exact nature of this capability depends on the specific object. So this is what's called dynamic lookup. When I invoke a function f, even if the variable is pointing to the parent type b, the actual subtype a will determine what the effect of f is on that particular object. And finally, we saw that very often subtyping coincides with an idea of inheritance. So when a is a subtype of b, we can also reuse parts of the implementation of b in a. But the example with the deck and the queue and the stack shows that technically speaking, reuse of implementations is not always compatible with a subtyping thing. But in practice, what we will find is that in the languages that we looked at, Python and the language we are going to look at, Java, there is only one way to organize these types. There's only one hierarchy. We don't have a subtyping hierarchy separately and an implementation hierarchy separately. So we have to live with whatever we can do within that one thing. So usually we will go with the subtyping hierarchy and we will just do whatever reuse of implementation is allowed there.